All right, we are moving into chapter 23, which is on geometrical optics. All right, there's not too much of geometry in it, but optics, that's what you're doing. So it's all about light. So what we end up learning in this chapter is reflection of light, and then we study about mirrors, and then the different kinds of mirrors, and then we study refraction, and then we move on to lenses, your lenses that you're wearing. We move on to that, a bunch of calculations on it, and that's what this whole chapter covers. So it's mainly reflection and refraction. So geometrical optics includes reflection and refraction. Okay? Refraction need not be only through lenses. Refraction can be through any solid surface like prisms and blocks and stuff like that. All right, so let's begin. Starting off with reflection. Now, there are two models that can be used to study reflection or refraction. The first model is the true model, which is called the wave model. Okay? Wave model. And the other one is called the ray model. You know from last year we did waves, right? We did the basics of waves. So wave model talks about a source which generates waves, right? So a set of waves are generated, and these waves keep moving out like that. What are these lines called? What are each of these called? Huh? It can be the form of crests and troughs and stuff like that, but what is each of those? Any wave fronts? You see that? No. Did you hear the word wave front last year? I must have used it, but anyway. Wave front is the locus of all the points that were generated at one time. So let's say, for example, I create a wave. Where is that wave after 1 second? It's gone 340 meters all around me, right? So if I'm going to click, if I do that, what's happening is I'm sending sequence of waves, and they're traveling at a certain speed. What's the distance between each wave front?
Frequency or wavelength.
Wavelength. The distance between each of these is called a wavelength, lambda. Frequency is the number of them generated per second. Right, Sam? Okay. Lambda is the wavelength, which is the distance between two waves, and frequency is the number of waves generated every second. And these are called the wave fronts. What's a wave front? Each wave front is the locus of all the points generated at a certain time. So these were all generated at one time. The next one was generated after a period of time. One period. So the time between these two is one time period. You know time period, right? Okay, so the time taken for, after how long is this one generated? After the first one is after one time period. And in one time period, the wavefront moves the distance of 1 lambda. So these are some of the basic stuff of waves that you have done last year and forgotten at the same time. So bring back your memories on waves. We will need this, not for this chapter mainly, we'll need it for the next chapter very much. Okay, so for this chapter is all right. So that's a wave model. This is the true model. Waves actually move in this manner. Now, what is a ray model? A ray model is, that's a source. The energy is produced from there, and in which direction is this energy moving? The energy is moving in this direction, outwards. That's called a ray model. So drawing these rays. So these are rays. Now what is a ray, by the way? A ray is an imaginary line drawn to represent the direction of motion of a wavefront. So which way are the, so these are the rays. See, these are the rays. So a rays are imaginary lines representing direction of waves. So the wave is the actual true thing, but rays are just for simplicity. It's easy to draw it. Like when you're small, when you're told to draw the picture of a sun, you normally kind of draw a circle, put some smiley and all that, and then what do? You kind of draw lines going out from the sun. There's nothing going out like that from the sun. Those lines are all imaginary, but it actually kind of tells you some important information that is like something is coming out from there. So that's why you draw these lines that way. So this is a ray model. Now, using the wave model, showing reflection is kind of hard. Okay, demonstrating reflection using a wave model is pretty hard. Let's say for example, if there is a reflecting surface like a wall, there's a mirror, there's a reflecting surface. So what happens is this, look, the waves are coming in. So the waves are coming in. So this part of the wavefront first hits the mirror. What will happen to that part of the energy? It bounces off, whereas these things are still moving forward. Okay? So after a period of time, by the time this one goes and hits here, and by the time this goes and hits here, this one must have bounced back here. So after reflection, this is here, this one was here, and this one is here. So this is the reflected wave. The wave is getting bounced. And what will happen to the reflected wave? The reflected wave will keep moving like that. The reflected wave moves this way. The actual wave started from here, but the reflected waves are going this way. Now, for an observer standing on this side and watching these things coming, these things appear to have started off from somewhere. Where are these appearing to come from? These are appearing to come from there, correct? These things are appearing to be coming from this spot. But they are not really coming from here, they're coming from here. So these waves are appearing to come from here. So that becomes an image of the source. An image. That's the actual source. And this becomes an image. And what does the word image mean? Image comes from which word? Imaginary. Image. It's just an imaginary thing. Okay, so image. So these things are coming, appearing to come from there. They're not really coming from there. There's nothing on that side. But it's only appearing to come from there, and that is why it's called an image of what? Of the actual source. Now see how complicated it is to draw this. That's why the ray model is adopted by us. Now, if reflection is going to be so tough with a simple plane surface, now what if the surface is curved? It makes it still complicated. So the best thing to do then is not to stick to wave model, although you know that wave model is the real thing. We just don't use the wave model for drawing purposes. It's much simpler to study reflections and even refractions using the ray model. So the ray model is very easy to study, and that's what we're going to use. So starting with the basic thing, reflection, plane mirrors. Okay? So what happens in a mirror, in a highly polished surface? When you have a highly polished surface, mirror, when a ray comes and hits like that, we call this incident ray. Incident ray, the incident ray that's coming in. Again, remember, there is no such thing as rays, it's waves. So it's like this. It's waves coming like that. And then it's tough to draw that. See, that's actually what's happening. Waves coming like that and bouncing off. But since it is harder to draw that one, we use the ray model. So incident ray is a ray that comes and hits here. Now this line is a perpendicular line to the surface and it's called the normal. These are all terms that we'll use very frequently in this chapter. That is a normal. And what's a normal? It's a line that is perpendicular to the surface. So for this table, the normal is like this. And the reflected ray is that. That's a reflected ray. Now, using wave model, we can geometrically prove that the angle of incidence is equal to the angle of reflection. So angle of incidence, I, is equal to the angle of reflection, R. So angle of incidence is equal to the angle of reflection. And this can be proved geometrically using wave model. Okay? It's an easy proof using similar triangles. Okay? Coming in, bouncing off. So it's not difficult to prove that one at all. We will use some of those concepts in refraction. So when we do refraction, then I will show you the proof. But for reflection, it's very easy. So angle of incidence is equal to angle of reflection. Yeah.
What allows a mirror to not absorb the light and just reflect it back?
Absorb.
Instead of
Every surface has got a proportion of absorbance and reflectance. So a mirror is designed to kind of throw everything that comes on it. But again, a plain mirror is not a perfect mirror. It is not.
What gives it that ability to do that?
It is how well, it all depends on the material and what is actually pushing the light out. Like if you look at this glass, it's not a good mirror, so you can see dim, on the door. You can see images, but it is kind of dimmer. The reason is the light that goes from here is 100%. What's coming out from there is probably just 20%. What happened to the rest of them? Rest of them could be transmitted, means going to the other side. If somebody's standing on the other side, will they be able to see you? That means transmission and absorption. probably like 75% transmission, 5% absorption, and 20% reflection. That's what's happening there right now. But the percentage of what is getting bounced back and all that depends on so many factors. Okay, so different surfaces reflect to different. So yeah, there are three terms: absorption, transmission, and reflection. So the percentage of which one is better? Well, if you want transmission as the most important thing, then we need 100% transmission. We don't want reflection in that, right? So if you want a plain glass and you want to see through it properly, but you need a good transmission coefficient, not absorption or reflection. You don't want it to get reflections. All right, so yeah, this is angle of incidence and angle. Now, all these angles are measured with respect to the normal. Remember that. Angles are always measured to the normal. That's why the normal is a good reference here. So this is not the angle of incidence. Okay? So even if I drew a mirror like this, and I said a ray is coming and hitting at an angle of 30 degrees, that's not the angle of incidence. What is the angle of incidence? 60. So you have to understand that angle of incidence is always the angle with the normal, so that's actually 60 degrees. So don't confuse with any angle that is shown in the diagram. You have to understand that angle of incidence is the angle always with the normal. Okay? So the angle of incidence is equal to the angle of reflection. So these are the laws of reflection. So the laws of reflection. This is the first law of reflection. That's the first law of reflection. The angle of incidence is equal to the angle of reflection. And the second says the incident ray, normal, and reflected ray lie on the same plane. They lie on the same plane. Incident ray, normal, and the reflected ray lie on the same plane. That is a law. So when reflection takes place, this is what happens. So this is a normal. If this is a normal, if this is the incident ray, reflected ray has to be exactly along the same plane. Right? You understand? So the reflected ray, the normal, and the incident ray, they should be in one plane. And what it means is you can't have a ray coming and hitting like this on a mirror and then bouncing that way. You get it? So it can't go like that. It has to go exactly to the other side. So the incident ray, the normal, and the reflected ray should be along the same plane. Yes?
And these laws only work with plane mirrors?
It's a law. It should work everywhere.
So any kind of mirror?
Any kind of mirror.
Okay.
Good or bad. Any law that Kentucky makes is not for just for good people. It's mainly for bad people, right? Anyway, so this kind of reflection. So this is the law of reflection. Now there are two kinds of reflections. Let's look at the two kinds of reflections. There is a reflection called specular reflection. And there is diffused reflection. Specular reflection and diffuse reflection. Now what is a specular reflection? If the surface is absolutely smooth, and if you have a bunch of rays coming and striking, these are parallel beam of light. Parallel beam of light. If you have a bunch of parallel beam of light, what is that?
Yeah.
All right.
I don't know. Dude, I'd walk.
Um,
Somebody walking. Yes. As it goes forward out of,
All right, coming back to this parallel beam of light coming and striking this mirror, what will happen to all these rays? Now, where are the normals? The normal is here, the normal is here, the normal is here, the normal is here. So, do you think the angle of incidence is exactly the same for all of them? Is the angle of incidence exactly the same? Yes, because they're all parallel. So obviously all the angles have to be the same. So what will happen to the reflection? They'll all get reflected exactly similar.
Please disregard the bell that just rang. We're putting it back on the right schedule. Please disregard that bell. We're still in first period. Thank you.
So there's a parallel beam of light coming and hitting the surface, and it bounces off exactly the same way as it came. And that's called specular reflection. Now, what is a diffuse reflection? The surface is not smooth. And if you have a bunch of parallel rays of light, so that's a parallel beam of light coming and striking it. What happens over there? Are all the normals exactly upward? No, because the surface itself is like curved. So the normal over here is probably like this. The normal here is probably like this. The normal here is probably like this. The normal here is probably like that. The normal here is like that. The normal here is like this. The normal here is like that. So the normals are all at different angles. So what happens is the angle of incidence here is different. So this one goes like that. That one goes like that. That one goes like this. This one goes like that. That one goes like that. That one goes like that. It just scatters the rays. So the reflected rays are not parallel anymore, right? They just scatter, they diffuse. They're not orderly at all. After reflection, they're not orderly. And that's why it's called diffuse reflection. So specular reflection is when you get exactly the expected outcome. And the other one is like after it hits the surface, it just scatters it and diffuses it. And which one is important? Which one is more useful to us? Specular or diffuse? Well, you need both. You need both. Like, if you want to see yourself in a mirror, you are looking for a specular reflection because you want to see exactly the way you are. So the light that goes into the mirror, it has to bounce back exactly the same way. Otherwise, it'll be out of shape. Right? So if you want to use a telescope or if you want to use an optical device, you are looking for a specular reflection. Why? Because you want a certain geometrical pattern to be followed. Okay? You want the light ray to bounce and go in a certain direction, which means you need a specular reflection there. Diffuse reflection, very, very important also. What helps you to look at the book and read? How am I reading the book? Because of diffuse reflection. Because imagine the book is absolutely like a mirror. I won't be able to read this. Because when I look at the book, the ceiling will be seen there. I can't see what I'm trying to see. Instead, I'll see the ceiling bouncing off. This board is diffuse reflection. Like this surface is not absolutely like a mirror. It's not polished. Although it looks smooth to me, it's got lots of tiny ups and downs, like matte finish. Yeah, by the way, photographs. When you want to print pictures, it'll ask you want glossy print or a matte print, right? Have you seen them? No? Have you printed any pictures anywhere? No? Okay. Should try all those things. You go to Meyer or Walgreens or somewhere and then, get those prints. And obviously when you come to final printing thing, it'll ask you want a glossy print? Okay, have you seen a glossy print? Pictures which actually is like shiny. like absolutely shiny pictures. And a matte finish is, again, it's also on a photographic paper, but it is not reflective. You can see it's like rough. The surface is rough. Okay, so that is a matte finish. Now, the advantage of matte finish is that you can actually keep it under light and you can see it without any light bouncing on it. It will just, you're able to see things straight away from the picture. No other light will bounce right into your eyes. And so it is a better one actually. Glossy print is always a hard thing. You know, you always have to keep it at the right proper angle in order to see it. Okay? Same with screens. If you have a television screen, see, the television screen is not 100% reflective. If it is 100% reflective, what will happen is when you look at the screen, you'll see yourself there. You want to see what is inside, not what comes from the outside. Right? So you don't want a screen to be having a very fine finish. Some laptop screens are glossy, and some laptop screens are matte. Like, you won't see reflections on it. Have you noticed anything like that? Yes? Check it out. Next time when you see anything, you know, look for how it is. I think there are some screensavers or whatever. Not screensavers. What do you call this? The thing that you put on top. Huh? Screen protectors, yeah. The screen protectors, some of them are not glossy. Now this is glossy. This is glossy, right? You can see yourself in it. You can see the shine coming out. There are some which won't get you the shine. That's a good thing. Because when you're trying to see something and then if this light is kind of staring at you, then of course it's not going to be clear. So you need to kind of change your angles, right? So yes, diffused reflection is very, very useful. Imagine it's all specular everywhere around us. Imagine it's all like mirrors everywhere. On the floor is mirror, on the top is mirror, everything is mirror. It'll be a terrible life. You'll get totally confused because you don't know where you're looking. Because wherever you look, you'll see all your friends everywhere. Okay, so it will be too much. Yeah, I mean, like, have you gone into those mazes? What do you call that again? Yeah, house of mirrors and all that. Yeah, so the moment you enter, then from that moment onwards, you're seeing mirrors and you don't know whether you're actually seeing a hallway or is it just a mirror in front of you. And you start walking and you bump into a mirror. Then you'll realize that, okay, that is not the way to go. So you get totally confused once you're going there because you can't trust what you see. Because what you're seeing is probably just a reflection of a mirror. And you think oh, that's a straight way, I can just keep walking there. But you can't just walk because then there is a problem. Now they give you some gloves to wear. Have you been in one of them? Then they'll tell you to wear some plastic gloves because generally what happens is if there is some kind of a stain left on the mirror, then that stain will reveal that there is a mirror. Because when you're looking like this, as soon as you see a stain right in front of you, then you know, oh, that's a mirror. So that's why when people bump into it, then normally they use their hands and kind of, as you walk like this, you just touch, and they don't want to stain the glass, and that's why they give you those things so that you don't touch anything. Anyway, diffuse reflection and specular reflection, both are equally useful. We purposely make some surfaces in this style so that you don't want reflections coming from there. This board. Imagine this board was specular. Imagine the board is completely specular, like a mirror. What will happen is, instead of seeing these details, you will see yourself. There can't be anything more distractive than that. Imagine you see a mirror over here, you see each other, you'll be like waving at each other all the time. Because you see them there. There's a different, it's a fun activity basically. You see your friends inside a mirror, you always feel like waving, but they're sitting next to you, you don't wave. Yeah.
Oh, but wouldn't you see the marks that you make on the mirror?
You will see that also. You will see this one also, but you'll see the reflection. So these will look like as if it's suspended. Okay? So it will be very distracting. So again, when the windows are open, the light comes from there, the light bounces from here and then comes to your eyes. So the light will come into your eyes more than these. And that means, again, you'll have difficulty reading it. So specular reflection and diffuse reflections are two kinds of reflections. Both are equally useful, and we use them at appropriate places. In which of them are the laws of reflection obeyed? Both of them. Whether it's diffused or specular, they both obey the laws of reflection. Now what's happening over there is the surface is not smooth, the surface is deformed, and so the normals are deformed. So if these are the normals, if this is a normal, when the surface kind of bends around, then the normal shifts, and that will diffuse the image. Like if you're standing next to a lake, if you're standing next to a lake, and the water in the lake is absolutely not moving, still. It's absolutely still. What will happen? Somebody, the trees on the other side and all that will bounce off from there as if it's a mirror. It will look like a mirror because there's nothing to disturb it, right? Now, if somebody disturbed that water, what will happen is then the surface is like going like this. So the normal is shifting continuously. Everywhere the normals are different. So then what you'll see is nothing. It's diffused. You won't see the reflection anymore. If you've been to the Mammoth Cave or to Marengo caves, have you been to those caves? Now, since they are underground and all that, there are some places where there's a puddle of water. And if you watch the water, it'll be absolutely still because nothing is there to shake it. Okay, so it's absolutely no wind, nothing, and you can see it's like a mirror. You feel like it's a mirror, it's just like a mirror. That's because it is absolutely still, the surface is flat, really flat, and that makes it more like a mirror. All right, so reflections. Okay, so how is an image formed from a mirror? So image formation from mirrors. We do ray diagrams. So you see lots of ray diagrams drawn, so draw them also. So how is an image formed by a mirror? That's a mirror. This is an object. So from the object, rays come and hit the mirror. And then, depending upon where they hit, the angles are different. Which angle of incidence is bigger? This or this? Which angle of incidence is bigger? This is bigger, right? Geometrically. Yeah, this angle is bigger. And so the angle of reflection is also bigger. So what happens is this one bounces off and goes like that, making exactly same angles. And this one bounces off and goes like this, making exactly the same angles. So these two angles are alike, and those two angles are alike. And if you try to look at these from there, if you're looking at those two rays from there, where do they appear to come from? They appear to come from this point, and this is called the image. Okay. That is what is known as the image. So these rays start and hit the mirror, and then they bounce off, and they enter the eye, and it kind of deceives your eye, because the eye thinks that these rays originated from this point. And that's what we consider as the image. That's a point object. Now what if you have an extended object? If you have an extended object, then the ray diagrams will be a little more. We got it? So for extended objects, that's a mirror. Let's say this is an extended object. This arrow is an extended object. This is the arrowhead, and this is the tail of the arrow. So that's a mirror, and that's the arrow right there. It's an extended object, and then you look at the object through the mirror, how the rays are going to be formed. So you have two rays going from here. I mean, rays are going from everywhere, but we take the extreme points of the object in order to get the image. We always take the extremes. So two rays going from there, hit there, and forms an image this way. So your eye will be able to see, the head of the arrow here. Now where's going to be the tail of the arrow? Take two rays from here. The tail of the arrow is going to be here. So where is the image? The image is that's the image of the object. Now what are the characteristics of this image? What are the characteristics of this image? Formed by a plane mirror. The characteristics of the image formed by plane mirror. Number one, same size. The image is exactly the same size as the object. So if you're standing in front of a plane mirror, you will see yourself exactly your size. All right? You won't see yourself smaller or bigger. You will see exactly the same size if it's a good plane mirror. Second characteristic, it's at the same distance. It's at the same distance as the object is in front. So if the object is a certain distance in front of the mirror, the image has to be exactly behind the mirror, same distance. So if you're standing in front of a mirror and look at yourself, your image will be exactly the same distance on the other side. I'll continue with these two. There are some more characteristics to be added.